So in the last class we talked about AlexNet, then we talked about VGG networks, and now we discussed about InceptionNet. Okay, but as time goes on, new and better models and architectures keep coming. So today we will discuss about residual networks. So these networks are actually designed making sure in mind that we can go very deep in layers without actually having a lot of problems. So one problem that we know that happens while going very deep or increasing the number of layers by a lot is overfitting. But there are other problems as well, and we will be discussing about those problems, and then we'll understand why we require residual networks and how the actual architecture is. First we'll discuss about the module though. So here we have a simple AlexNet network. Okay, so ideally what should happen is, if you think about it, if you increase the number of layers, the accuracy should increase. Right, that is the most ideal solution that we always know. Increasing the number of layers, going deeper, will increase the accuracy, but that is not the case. So residual network, the paper shows that here you have the training error. This is for 20 layers of AlexNet. Then again they have trained the whole same thing on 56 layers of AlexNet, and you can see very easily that the training error is way high for 56 layers, although this is a more deeper kind of network. So what is happening exactly here? Also you can see the test error also. The 56 layer does not perform that good as compared to 20 layer. However, 56 layer is a more deeper kind of network. So what is the problem? What exactly is the problem? Okay, so first thing, obviously we have overfitting, but then we have come across ideas how we can prevent the overfitting. So overfitting is not the only problem that we are having. That means this problem is known as network degradation. So what that means is, if you increase the number of layers, your network is going to degrade. That means it is going to perform in a worse form. But in theory, we all know, in theory we have all read that when you increase the number of layers, it should ideally increase the accuracy or decrease the loss. But then there is something that is lacking in the network problem or in the training or practical problem that is causing us these problems. So we will be looking into what is happening. So about network degradation, this happens due to gradient explosion or vanishing gradient problem. If you go back in the classes, you might remember I talked very little about this vanishing gradient or gradient explosion problem. When I was talking about back propagation, the problem that we were having is, let's say you have 34 layers, right, and you are back propagating the whole loss and to update the weights. So for updating you are following the chain rule. That means this is all multiplication. So W1 by W2, this should be the output ideally, and then this goes on, right? So let's say DL by D output 1 into D output 1 by D output 2 into D output 2 by D output 3. Now if this is a 34 layer and you have to go very backwards, so this is a very big multiplication. And if your weights or these values are updated very little, let's say it is even 0.1, and now this is being, let's say all of these are 0.1, and this is now being updated 34 times. So 0.1 to the power 34, this basically comes out to be nothing. That means 0.1 to the power 34 is a very negligible value. So that means this is very close to 0. You are not updating the value in any way. This is known as a vanishing gradient problem. That means these gradients, because of these gradients, the chain rule, the whole gradient thing, the whole update thing is getting vanished, hence vanishing gradient. Now gradient explosion, what does that mean? So what gradient explosion means is that the gradient becomes very large. So let's say here it was 0.1, you have the same thing, dl by do1 into do1 by do2, do2 by do3 and so on, right? So if suppose instead of 0.1, let's say we have 2 as the update value, so now 2 to the power 34 is way much, it's very big, it's a very large value, right? So what will happen in that case is the gradient will go very high. Since the gradient goes very high, your update is massive. So let's say here you have the plot, you have to reach the minimum value, your weight is somewhere here. Now the gradient value is very high. So in that case what will happen is it will skip the whole part and come somewhere here, let's suppose. And then again you update, but since this is a very big multiplicative problem, here again it will skip and maybe let's say it comes here. So what will happen is it will just keep bouncing back here henceforth and it will never be able to reach the minimum value. This problem is known as gradient explosion problem. So we understood the vanishing gradient and the gradient explosion problem. So this happens because you increase the number of layers. Now I showed for a 34 layer. Imagine it's a 56 layer. Now you can understand why we are having this problem, and this leads to the degradation of the problem. Hence we call it as network degradation. Okay, so this is basically caused due to gradient explosion and vanishing gradient problem. So to solve this problem, what the researchers did were they come up with a very brilliant solution. So they came up with something which is known as a residual block. This is known as a skip connection. We'll discuss everything. So what happens is basically, suppose you have the x here, so you will do the whole convolution or weight a layer in like MLP or whatever. So you will pass the whole thing to a layer, then you will do an activation function and pass it again to another layer. Okay, so this thing basically is the basic neural network structure. So you are passing it here, this thing, and you will pass this here. Here what will happen is you will have an addition. So this addition will be basically the output that you get from here, that is f of x, plus this here, this connection. This is a skip connection. So you will add this part here. Now what this is doing is, we will talk about that later, but this is known as a skip connection and this is very helpful. And this is also known as identity mapping. You might heard of identity mapping in the functions chapter when you were learning in class 11 or something. So in that case what used to happen is f of x would be equal to x. I suppose that was the case. So here also what they are doing is they are adding a skip connection here. So you do not have just f of x, you also have a plus x here. And now this will continue on with the same layers one after the other. So here you will have again the weight layer. This is x. This again will pass through another weight layer. And you might have another skip connection here. Okay, but here one thing that you should remember very properly, okay, this thing is a bit different. Here you have first addition, then it is followed by a ReLU. This is very important to remember. I'll tell you why also again, but yeah, just remember that first you add and then this is passed through an activation function. So let us break down to what is happening. So what happens is you have these gradient explosion or gradient vanishing gradient problems. So what this usually means is sometimes some layers might not be important or those layers might not add a lot of value to it. So let's say this is one of those layers where you are not getting a lot of features from there. So in that case what will happen is these will contribute to either gradient descent or vanishing gradient problem. Since these make no sense, why don't we just skip that layer? So in the back propagation problem, you can probably, let's say this layer here is not adding a lot of use, so we can totally skip this layer and we can go to the next layer. So in that way, if this is not adding, we can skip that layer. Now what this means is you don't have to deal with 34 multiplications. This narrows it down and it gives importance to whatever whatever network or whatever layer is important. So the number of multiplications get reduced and hence it is very useful. Okay. So basically this whole skip connection, this acts as a regularizer. If you remember, we talked about regularizers and they were usually required to prevent overfitting. But in this case, they are required to prevent network degradation. Okay. So now what will happen is, let's suppose this layer is not very important. So you have X, this will go on, you will add, and you will add the whole layer output with X. If this is not important, this will technically be very little, so your more focus will be here on X part rather than on the FX part. Hence, even if we increase the layers, what will happen is these layers will be of not a lot of use, so that the model can itself decide if this is required or not required, and then it can keep changing. So you need to first add and then this is followed by a ReLU. So this is very important. You need to add and then that is followed by a ReLU. Now let us look at its structure. So here this is a basic ResNet structure. So residual net is also known as ResNet. So here this is a basic VGG19 structure and this is a 34 layer plain network. That means here you have 34 layers but there is no residual blocks. Now here you have the same thing but here you have different residual blocks. See, these are all skip connections. These connections are known as skip connections. So this goes on for 34 different layers and till the end you have then final fully connected layer and so on. Now let us look into some other things. So this is what we get when we finally train the ResNet structure. So this is a plain structure. This is a plain network. So here you have a plain network for 18 layers and then you have a 34 layer. So you can see the blue one represents the 18 layers and here you have 18, but the 34 layer is having more error than 18 layer structure. You can see this is the basic one that we had. After adding residual blocks, what happens is you can see the 34 layer now has less error than 18 layer. So what did happen is it helped in reducing network degradation. So now, like the VGG that we studied, it had many different layers. You had 11, you had 13, 16, 19. In the same way, ResNet has many different layers. It has 18, 34, 50, 101 and 152 depending upon what is required when. So here this was given obviously in the research paper, and here you can see how they have made the 18 layer, 34 layer, 50, 101 and 152 layer. So the main thing is it starts again with 7 cross 7. If you remember, Inception also started with 7 cross 7. Then you had 3 cross 3. This is one max pooling, and then final structures are more or less the same. The number of blocks keep adding. So what will happen is, if these blocks are not important, since you are adding this here, this part skip connection you are adding. So what this does, it just totally skips this part, as the name suggests obviously. So you will not have to go through this whole thing. So if these layers don't make a lot of sense, you can just totally skip them. That is the whole point of this. So you can add more layers, but at the same time you will be able to skip them if they don't make a lot of sense. So here you can see the architecture is more or less the same. What will happen is they are using here into 2 times, into 3 times, 3 times, 3 times. I mean the number of times that layer is being used gets increased depending upon the total layer of the architecture, right? Now here what they have done is we have a skip connection, but this is a skip connection that makes sure that you have an optimized network or optimized block. So what that means is, basically, if you remember, we add 1 cross 1 to reduce dimensions. So here, instead of 2 3 cross 3, it has done 1 cross 1 followed by 1 3 cross 3 and then again a 1 cross 1. So basically these 1 cross 1s help in reducing the number of trainable parameters. Trainable parameters reducing. So that is what this whole thing is about. Now this is an optimized version of the network. And like Inception Net, what will happen is residual network itself has many different variations from time on. It has been improved. So you have ResNet v2, v3 in the same way that you had Inception Net. And in the next class, we will actually learn about the different Inception Net variations, how from time it has been improving. So just a recap, we started with AlexNet. So in AlexNet, what usually they did is they had a convolution which was followed by max pooling. You had 5 convolution, I suppose, and 3 fully connected layers in AlexNet. Then they had VGG networks. So in that case, what they had 2 to 3 convolutions, one after the other, and then it was followed by a max pooling. Okay, and then we went across Inception Net. Inception Net basically focused on giving more structure in the wider appearance rather than going more deeper. So it had 1 cross 1, then it had a 3 cross 3, 5 cross 5, and then a max pooling. And this was the previous layer, let's suppose. So you connect all these, and then finally here you have the next layer. So this was the whole thing about Inception Net. So what this did was help in reducing the number of parameters, at the same time increasing accuracy. This is one of the best engineered networks. And finally, now we are talking about residual networks. They solve the problem of network degradation. Now each network on its own has some pros and some cons, right? But for the time that they were invented, when they were created, the whole thing, they actually made more sense and they were the best at that time. But as we go on, the models keep on increasing. So we need to, as data scientists, keep ourselves updated with the new models, and in which case what model will be required, this we need to make sure of. So hence we should actually understand how it all started. I mean, right now the best architecture that is being used is nowhere close to any of these architectures. But it is still very important that we know about the history of how these networks started. Hence, we should know about all this. And obviously, these are very much asked in the interviews. So in the next class, what will happen is we will understand Inception Net later versions. And then we'll understand the residual net later versions. Then we will also see a combination of Inception and residual net in the final one. And there is also something which is known as V transformers. These are very new. The paper came out recently last year and they have actually blown the market. People are actually using it, and this is very much related to language processing. So once we understand language processing, how all of this work, we can go back and come to how vision transformers also work. So with time, obviously the networks keep changing, like I keep saying, and so we need to just be updated with everything that is happening. So that is it, and enjoy learning and have a good day.